$1,000 price tag remained a tough sell.
What we did to get people started, we would rent the robot. You'd hire it, like a person. And we would say, at that time I said it's $6 an hour, I think, for the first shift, and $3 an hour for the second shift. So your labor gets cheaper.
The robot had one thing advantage immediately, and that is the robot can work 3 shifts or work 24 hours a day.
George and Joe set out to change public perception of the new machines. They took their robotic show on the road.
Would you welcome Joe Engelberger? Joe?
And ultimately, the show that was so important to us was the Johnny Carson show. And that's where the idea was, suppose we try to give the impression that the robot could do the whole show. So you had the 3 scenes. 1, it could play better golf than Carson could.
Is that wild?
2, it could do the beer commercial better than anybody.
You see, in case you get tired and can't make it to the show someday, we can program the machine to do a commercial.
And 3, lead the orchestra.
Now, what he's doing now is to program what he's going to have the machine do. He's putting this information into the machine.
And that gave me a chance to show how the arm moved with a baton.
Take it on the downbeat.
The public loved the Unimate, but industrial orders did not pour in. It took Unimation 14 years to make a profit. But there was another market that saw the potential of robotics: the Japanese. Theirs was a nation in need of a labor force, and they immediately embraced the potential of robots.
The Japanese outclassed us in quality and cost and manufacturing and features, and that's where the difference was made. If I talked to an American executive, they want to know how fast they're getting their money back. The Japanese would look long range.
Kawasaki and Unimation formed a joint venture. The Japanese quickly took the lead in the robotics industry. While American industrial robot companies struggle for survival, at universities around the country, researchers work to make robots smarter. At MIT, Norbert Wiener invented the science of cybernetics, a word coined from the Greek meaning governor. More than being run by complex computer programs, these cybernetic creatures appear to respond like simple animals and learn just by reacting to a variety of basic stimuli, such as light. Independently of Wiener, British neurophysiologist Gray Walter created the famous cybernetic turtles in the late 1940s. These robots experienced the world with phototubes, microphones, and contact switches, and could navigate through the environment. One of the most impressive of all cybernetic animals was known as the Beast. It was built in the early 60s at Johns Hopkins University's Applied Physics Lab.
The environment in which this vehicle is to live is that of the halls of the Applied Physics Laboratory. There it must cope with the various obstructions around the wall while seeking out sufficient power outlets from which to keep the battery charged, which are located in the lower part of the body section.
Beast's goal was continuous motion and unassisted survival in this environment. Equipped with sonar, a photocell eye, and tactile sensors, it managed very well.
During the working day, most office doors are left open. It is desirable not to allow the device to enter these offices and must, therefore, sense the door jamb, bridge the open door, and regain acquisition with the wall.
It could even prevent itself from falling down stairwells. When trapped, it went into a vibratory mode to shake itself free. The beast had no real brain, just sensors, but its electronic behavior patterns allowed it to survive in the world. This bottom-up approach of achieving the bare rudiments of intelligence with simple models of animals was soon eclipsed in the early 1960s as a new field took hold: artificial intelligence.
There, miss. You see the heterodynes are feeding back into the stimulus reaction activators, causing non-snaps of the motor control resistor units.
Oh, that's good.
No, lady, that's bad. But your regenerative circuits are tuned asynchronously, and that causes concatenation in the intermediate amplifiers.
Well, that's bad, isn't it?
No, that's good. From now on, I don't think there'll be the slightest trouble with your robot. Your domestic problems are completely solved.
No one ever thought it was going to be easy, but building an intelligent robot remained the holy grail that challenged and tormented some of the greatest scientific minds for the latter half of this century. The advent of digital computers in the 1940s suggested the way forward. In America, ENIAC, the first supercomputer, was a giant brain composed of a room full of vacuum tubes. It was built in 1946 to calculate the trajectories of artillery shells. At the same time in Britain, mathematical genius Alan Turing was working on the Turing machine, a theoretical device used to process equations without human direction. The idea of mimicking human mental abilities through electronics was born.
His goal, as was the goal of all of the people who started in the field, was to achieve human-level intelligence. And he thought that computers would be able to play the imitation game, that is, would be able to successfully pretend to be human over a teletype line by the year 2000.
At a conference at Dartmouth College in 1956, Professor John McCarthy coined the term artificial intelligence, or AI. This conference inspired AI researchers at MIT, such as Marvin Minsky, to lay the groundwork for computerized thinking machines. They devised programs that could play chess, recognize different shapes, and solve logistical problems. Claude Shannon created a remarkable experiment called the mouse in the maze that appeared to learn. Driven by a motorized electric magnet, its path was recorded by a computer that remembered only the successful parts of the journey. On its second attempt, the mouse finds the target easily, in a fraction of the time. In 1963, McCarthy moved to Stanford University and established the Artificial Intelligence Laboratory.
One of the major things that we undertook to do was robotics, and in particular computer vision in connection with robotics.
AI researchers figured that for programs to perform more like humans, they needed to be coupled with hardware to see, hear, and feel. Robot arms attached to TV cameras could perform very rudimentary tasks, such as moving colored blocks. But a dreadful paradox became apparent. While AI computer programs could easily outstrip human performance at calculus, when coupled with a mechanical appendage, they could barely achieve the hand-eye coordination of a toddler. Giving the basic sensory perceptions our brains accomplish effortlessly to robots was proving to be a Herculean task.
In hindsight, of course, it's obvious that those are actually the hard parts, because those are the things that human beings have done as a life or death matter for most of our evolution.
Yet while other labs struggled with these problems, Stanford Research Institute, or SRI, made history in 1969 by producing